Hi, my name is Sarah Spall, and I'm a PhD student at Indiana University. And I'm here to talk about Build Systems with Perfect Dependencies, which is joint work with Neil Mitchell and my advisor, Sam Tobin-Hochstadt. Let's start with the basic question of what is a build system. A build system describes how to set up a system from source code. It lists commands to run and dependencies to respect. For example, this make build script says how to build the target main.exe, which depends on the targets main.o and util.o. We could also consider a shell script to be a build system. This script also says how to build main.exe, main.o, and util.o, and its commands are ordered in a way that respect the dependency main.exe has on main.o and util.o. But a shell script lacks some of the advantages of a build system like make. Namely, a shell script doesn't provide incremental rebuilds or parallelism. A build system like make provides incremental rebuilds by requiring the user to specify dependencies for each target. Once again, in this example, main.exe depends on main.o and util.o, which each in turn depend on their respective C files. On a rebuild, if main.c changes, make will rebuild main.o, which will in turn cause main.exe to be rebuilt. And of course, the advantage here is that util.o was not rebuilt because its dependency util.c hasn't changed. Another advantage of a build system over a shell script is parallelism. Again, in our example, main.o and util.o do not specify dependencies on one another, and so they can be built in parallel. What are the advantages then of a shell script? In many cases, it is simple to write the series of commands to execute to build something. We don't need to think deeply about every dependency of what we're trying to build, we just say how to build it. Another advantage is the dependencies of the commands in the script can change, but as long as the commands themselves are still correct, the script will still build the end target correctly. If util.o gained additional dependencies on string.h and math.h, the build script would still build main.exe correctly, whereas the make build script will no longer rebuild correctly unless its dependencies are updated. So here, explicit dependencies would need to be added to the util.o target to main.h or to math.h and string.h. And of course, the disadvantages of the shell script are that it doesn't provide incremental rebuilds or parallelism. Each time the script runs, every command is executed, and commands, they just don't run in parallel. In this paper, we propose a new build system called Rattle that provides the benefits of a build system like make, but maintains much of the simplicity of a shell script by not requiring build script authors to specify dependencies. Rattle is a forward build system, and in a forward build system, build scripts have no explicit dependencies, and commands are just executed in the order they are listed in the script. Previous forward build systems, such as Memoize and Fabricate, have provided incrementality, but have not provided parallelism without requiring the user to annotate which commands it is safe to run in parallel. Rattle advances on these previous forward build systems by providing parallelism without requiring specific parallelism annotations. A Rattle build script is a Haskell program, but the build system itself has no knowledge of the logic of the build script. The build system only sees the commands that the build script supplies to the build system. The Haskell program supplies commands to the build system via the command function, a usage of which is highlighted in orange in this example. The commands given to the build script can be generated dynamically and determined by control logic the build system has no knowledge of. Therefore, the build system doesn't know which commands it will be asked to execute next. The Haskell control logic is run every time the build script is run, and every command is passed to the build system, and the build system then decides whether or not the command should execute. The build system must consider whether to execute every command generated by the script each time the script runs, because it has no knowledge of which commands the build script will want to execute, and it doesn't track whether the build script has changed since it was last run. How does Rattle provide incrementality and parallelism without requiring build script authors to specify dependencies? It does this by recording the file level dependencies of the commands it runs using file system tracing. Every time Rattle runs a command, it traces the system calls of the command. Therefore, each time a command runs, Rattle learns its most recent dependencies and will learn if a command's dependencies have changed since it was last run. Continuing with our example, here are some potential system calls that would be traced when Rattle executed each of the commands from the example. If we look at the first command, the command on the left, this command likely read both main.c and gcc and wrote to main.o. In this example, both main.c and gcc would be recorded as read dependencies of gcc-c main.c. And if either of those changed, the command would be rerun. On rebuilds, Rattle will check to see if the files read and written by each command have changed, and if so, it will rerun the command. For example, if main.c changes, Rattle will rerun the first command and would then rerun the third command if main.o changed as a result. Rattle provides two ways to achieve parallelism. First, users can explicitly tell Rattle to execute commands in parallel. In the example, the line highlighted in orange is showing the use of for-p, which is used to pass the generated GCC commands to the build system in parallel. Additionally, Rattle provides implicit parallelism. During the first run of a build script, Rattle cannot execute the build script in parallel because it has no file dependency information about the commands it is running. But on subsequent runs, it can try to achieve parallelism via what we call speculation. Using information about the files that each command reads and writes, Rattle can determine, in this specific example, that the first two commands can safely run in parallel, but the third cannot. To explain in a bit more detail how speculation works, remember that Rattle has no knowledge of the commands it will be asked to run during a build. Therefore, Rattle uses the command list from the previous run to try and predict which commands are going to be executed during the current build. And Rattle uses the information about which files a command read and wrote from the previous run to determine which commands it can safely speculate in parallel. Rattle runs commands from the previous build in parallel with the current build script. When the build system is asked to run a command by the current build script, if it has already executed that command speculatively, it can then skip it. This is how Rattle achieves parallelism. It is possible for Rattle to run commands in parallel that shouldn't be run in parallel. So let's talk about what happens in that case. Let us consider what would happen if these three commands ran in parallel. Every time Rattle runs a command, as mentioned, it traces the system calls of the command. So as we saw before, Rattle would learn that for each command shown on this slide, files listed below are the ones the command read and wrote. Every time a command finishes executing, Rattle compares the files read and written by the command to the files read and written by commands that previously finished. And it does this to look for what we call hazards. So for this specific example, Rattle would realize that the command building main.exe, the rightmost one, reads the two files highlighted in yellow. And the two commands it ran in parallel with write to those files. So Rattle's hazard detection that runs after every command completes would detect this. Hazard detection checks that commands executing in parallel, or that commands that executed in parallel only read from the same files and did not read or write to the same files. Hazard detection additionally checks that a command did not write to a file after it had already been read or written to by a previous command. If Rattle detects a hazard, currently it terminates the build. Rattle doesn't allow writes to occur after a read because on a rebuild where nothing has changed out after the build completed, no command should be executed again, and writes after reads or writes violates this. So here are two examples of this. On the left, we have an example of a write occurring after a read. It is problematic because on a rebuild, the first command will re-execute because the second command had modified its input. And the second command will run again because the first command modified its input. On the right, we have an example of a write occurring after a write. This is problematic because on a rebuild, even if the files read by the first command have not changed, it will still execute again because the output of the command was changed by the second command. And likewise, the second command will need to re-execute because its output, main.exe, has changed. Now I'll briefly discuss our evaluation. And for our evaluation, we built 5 projects that were originally built with Make with Rattle. Each project was built incrementally over a number of changes of various sizes with both Make and Rattle. The build scripts used for the evaluation of Rattle were static lists of commands generated by observing the commands Make ran to build the project. One of the projects evaluated was Redis, a data structure server which is available on GitHub. To compare the Rattle build script to Make, we built Redis across 26 commits from its GitHub repo. In this graph, our x-axis is the number of commits built so far, and the y-axis is the build time of the commit in seconds. So the x-axis at 0 is the time it took to build the project from scratch, and at 1 it is the time it took to build the project incrementally 1 commit later. So after the first commit, every commit was built incrementally. So from this chart, we can see that even though the Rattle build script had no explicit dependency information, its performance is still comparable to that of the Make-based build across all commits when built with a single thread. And here is a comparison of Redis being built with 4 threads by both Make and Rattle. Once again, the x-axis is the number of commits built so far, and the y-axis is time to build a commit in seconds. And from this chart, we can see that even though Rattle had no explicit dependency information, it still achieved performance and speed up comparable to Make for all but commit 0 in the chart. Because Rattle has no information when it first builds a project, it had no information on which to speculate, and therefore it had to build the project sequentially. So for further discussion of Rattle and things not discussed in this talk, such as implementation details of Rattle, of a longer discussion on system tracing, discussion of correctness, a lot more evaluation, and a discussion of related work, please read our paper. And thank you for watching, and if you're interested, Rattle is available on GitHub at the link on this slide, and we encourage you to go take a look. Thank you.